Before Isaac Newton, the universe was a mystery, a place where apples fell, planets moved, and light bent without anyone truly understanding why. Then, one man came along and rewrote the rules of reality. This is the story of Sir Isaac Newton, a thinker whose discoveries didn't just explain the world around us but fundamentally redefined it. From the quiet fields of Woolsthorpe, where a falling apple inspired a revolutionary idea, to the halls of Cambridge University, Newton's genius shattered the boundaries of human understanding. But Newton was more than a brilliant scientist. He was a deeply complex man, reclusive, obsessively driven, and locked in fierce rivalries with some of the greatest minds of his era. His breakthroughs in physics, mathematics, and astronomy laid the foundation for modern science, influencing everything from the Industrial Revolution to space exploration today. In this documentary, we'll explore the triumphs, conflicts, and inner struggles behind the legend. How did a solitary boy from rural England become the father of modern science? What led him to uncover the secrets of gravity, motion, and light? And why, after reshaping humanity's understanding of the universe, did he spend his final years chasing alchemy and decoding biblical prophecy? This isn't just the story of equations and experiments. It's a journey into the mind of a man who saw order in chaos, patterns in the stars, and laws that govern the very fabric of existence. On a cold Christmas morning in 1642, according to the Julian calendar, Isaac Newton was born in the small village of Woolsthorpe, Lincolnshire, England. A frail infant, he was so tiny that, as his mother later recalled, he could have fit inside a quart-sized mug. His father, also named Isaac Newton, had died 3 months before his birth, leaving the newborn as the sole heir to a modest family estate. Newton's early life was shaped by loss and feelings of abandonment. When he was just 3 years old, his mother, Hannah Ayscough, remarried and left young Isaac in the care of his grandparents. This separation left deep emotional scars that would later manifest in his solitary and introspective nature. Despite these early hardships, Newton displayed an exceptional curiosity from a young age. Rather than engaging in typical childhood games, he spent hours building intricate mechanical models, windmills, sundials, and water clocks, crafted from scraps of wood and household tools. These small inventions hinted at the mind of a future scientific genius. His formal education began at the King's School in Grantham, where he initially showed little interest in academics. However, a pivotal moment came when his mother pulled him out of school to manage the family farm. The experiment proved disastrous. Newton neglected the land and spent his time reading or conducting small experiments instead of working the fields. Recognizing his unsuitability for farming, his uncle, a Cambridge graduate, persuaded Hannah to let Isaac return to his studies. Back at school, Newton's passion for learning flourished. He soon outpaced his peers, driven by an insatiable desire to understand the natural world. These formative years laid the groundwork for a mind that would soon revolutionize science, forever altering humanity's understanding of the universe. In 1661, Isaac Newton entered Trinity College at the University of Cambridge, thanks to the support of his uncle, who recognized his intellectual potential. Cambridge, a hub of scholarly activity, exposed Newton to a world of new ideas, though the prevailing teachings still followed the works of ancient philosophers like Aristotle. However, Newton's inquisitive mind was already inclined to challenge traditional thinking. At first, Newton worked as a sub-Caesar, a student who performed menial tasks in exchange for financial assistance. This humble position didn't deter him. Instead, it fueled his determination. He devoured the works of modern thinkers such as René Descartes, Galileo Galilei, and Johannes Kepler, whose revolutionary ideas about motion, mathematics, and astronomy ignited his imagination. One pivotal figure in Newton's academic journey was Isaac Barrow, a renowned mathematician and the Lucasian professor of mathematics at Cambridge. Barrow quickly recognized Newton's exceptional abilities, particularly in mathematics. Under Barrow's mentorship, Newton's focus sharpened, and his studies deepened into the realm of advanced mathematics and natural philosophy. During this period, Newton began keeping detailed notebooks where he recorded his thoughts and experiments. These early writings revealed glimpses of groundbreaking ideas, including the foundational concepts of calculus, though Newton himself didn't yet realize the full importance of his discoveries. In 1665, Newton graduated with a Bachelor of Arts degree. Just as his academic career was beginning to flourish, a devastating outbreak of the bubonic plague swept through England, forcing Cambridge to close its doors temporarily. Newton returned to Woolsthorpe, where, in the isolation of the countryside, he would soon embark on a period of intense creativity and discovery. This period of solitude, far from academic distractions, would become the most productive chapter of his scientific life. In 1665, with Cambridge University shuttered by the Great Plague, Isaac Newton returned to his family's estate in Woolsthorpe. What could have been a period of stagnation instead became a time of extraordinary intellectual growth, an era Newton would later refer to as his Annus Mirabilis, or Year of Wonders. Alone with his thoughts and surrounded by the quiet English countryside, Newton began developing revolutionary ideas that would later reshape the scientific landscape. During these 2 years of isolation, he laid the groundwork for calculus, experimented with light and optics, and formulated his initial thoughts on what would later become the law of universal gravitation. One of his most iconic moments, though often mythologized, occurred during this time. According to legend, while sitting beneath an apple tree, Newton witnessed an apple fall. This seemingly simple observation led him to ponder a profound question. Why does the apple fall straight down? From this, he began contemplating the invisible forces that govern motion, an inquiry that would eventually lead to his theory of gravity. Despite these breakthroughs, Newton remained largely unknown outside his close academic circle. When the plague subsided in 1667, he returned to Cambridge and was elected a Fellow of Trinity College. Shortly after, his former mentor Isaac Barrow, recognizing Newton's superior mathematical talents, resigned his prestigious position as Lucasian Professor of Mathematics in Newton's favor. Even with his growing reputation, Newton was intensely private, often hesitant to share his findings. His reluctance stemmed from a deep fear of criticism, a consequence of his earlier emotional wounds. As a result, many of his groundbreaking ideas remained hidden in notebooks, waiting for the right moment or the right challenge to emerge. That challenge would soon come, pushing Newton to reveal the brilliance he had long kept in the shadows. As Isaac Newton settled into his role as the Lucasian Professor of Mathematics in 1669, his groundbreaking ideas slowly began to emerge from the shadows of his notebooks. His first major contribution came from his fascination with light and optics, a field that had long puzzled scientists. Newton's experiments with prisms led him to a radical conclusion. White light was not pure but composed of a spectrum of colors. By passing sunlight through a glass prism, he observed how it split into bands of red, orange, yellow, green, blue, indigo, and violet. When he reversed the experiment, sending the light back through another prism, he found that the colors recombined into white light. This discovery contradicted the prevailing belief that prisms colored the light, instead revealing that color was a property inherent in light itself. In 1672, Newton published his first scientific paper, New Theory About Light and Colors, through the Royal Society of London. The paper was met with both praise and criticism. Robert Hooke, a leading scientist of the time, challenged Newton's conclusions, sparking a bitter rivalry that would last for years. Newton, already sensitive to critique, withdrew from public scientific debate for nearly a decade. During this time, he continued refining his mathematical ideas, laying the foundations for what would later be known as calculus. Though his development of this revolutionary mathematical tool remained unpublished, his notes reveal methods to calculate changing quantities, concepts essential to modern physics and engineering. Newton's inventive spirit didn't stop there. Frustrated with the limitations of refracting telescopes, which distorted images due to chromatic aberration, he built the first functional reflecting telescope in 1668. This innovation used mirrors, instead of lenses, producing clearer images and marking a significant advancement in observational astronomy. Despite his growing genius, Newton remained reclusive. Yet with each experiment and discovery, he was steadily preparing to unveil a scientific revolution that would redefine humanity's understanding of the universe. By the late 1670s, Isaac Newton's intellectual pursuits reached their peak, culminating in discoveries that would forever alter the course of science. The spark for his most groundbreaking work came from a letter sent in 1679 by Robert Hooke, despite their ongoing rivalry. Hooke proposed ideas about planetary motion, which reignited Newton's earlier fascination with the forces governing celestial bodies. Newton began rigorously developing his theory of gravitation. Drawing on earlier thoughts from his Annus Mirabilis, he postulated that the same force pulling an apple to the ground also governed the motion of the moon and planets. This revolutionary insight led him to formulate the law of universal gravitation, the idea that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. In 1684, astronomer Edmund Halley visited Newton to discuss planetary motion. To Halley's astonishment, Newton had already worked out the mathematical proofs explaining why planets move in elliptical orbits, as described by Johannes Kepler decades earlier. Encouraged by Halley, Newton compiled his findings into what would become his magnum opus. In 1687, Newton published Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, commonly known as the Principia. This monumental work introduced three fundamental laws of motion: the law of inertia, an object remains at rest or in uniform motion unless acted upon by an external force; the law of acceleration, the force acting on an object is equal to its mass times its acceleration, F=ma; the law of action and reaction, for every action there is an equal and opposite reaction. The Principia provided a comprehensive mathematical framework to describe both earthly and celestial mechanics, unifying the heavens and the earth under the same set of natural laws. While the scientific community initially struggled to grasp the depth of Newton's work, the brilliance of his ideas soon became undeniable. His theories not only validated earlier astronomical observations, but also paved the way for the scientific revolution that would shape the modern world. The publication of the Principia in 1687 catapulted Isaac Newton into the highest ranks of the scientific elite. Almost immediately, his groundbreaking laws of motion and universal gravitation gained recognition across Europe, transforming him from a reclusive scholar into a celebrated figure. The Royal Society, which had once doubted some of Newton's earlier work, now hailed him as one of the greatest minds of his generation. His ideas reshaped the fields of physics and astronomy, offering a framework that explained everything from the falling of an apple to the orbits of planets with unprecedented precision. Even rivals like Robert Hooke, though reluctant to fully acknowledge Newton's genius, couldn't dismiss the clarity and power of the Principia. Recognition soon extended beyond academia. In 1689, Newton was elected as a member of Parliament for the University of Cambridge, though his contributions in this role were minimal. More importantly, he became a trusted figure within the intellectual and political circles of England. In 1696, Newton was appointed Warden of the Royal Mint, a prestigious position that brought him financial security and public influence. His work here was far from symbolic. Newton took an active role in reforming England's currency, leading efforts to combat counterfeiting, often personally overseeing investigations and prosecutions. By 1703, Newton's reputation had reached its zenith and he was elected president of the Royal Society, a position he would hold until his death. In 1705, Queen Anne knighted him, making him Sir Isaac Newton, an honor that solidified his standing not just as a scientist, but as a national icon. During this period, Newton also engaged in scholarly exchanges with Europe's leading intellectuals, including Gottfried Wilhelm Leibniz. However, a bitter dispute over the invention of calculus would soon test Newton's legacy and his patience. Still, despite personal rivalries, his influence during his lifetime was undeniable. laying the groundwork for centuries of scientific advancement. Despite his towering achievements, Isaac Newton's life was far from free of challenges and conflicts. His most bitter controversy arose over the invention of calculus, a revolutionary mathematical tool that allowed scientists to describe change and motion with unprecedented precision. Though Newton had developed the foundational concepts of calculus as early as the mid-1660s, he had not published his findings. Meanwhile, German mathematician Gottfried Wilhelm Leibniz independently formulated his version of calculus and published his work in 1684, years before Newton's concepts became public. A fierce dispute erupted over who had priority, dividing the European scientific community into rival camps: Newton's supporters in England and Leibniz's defenders on the continent. As president of the Royal Society, Newton used his influence to discredit Leibniz, even overseeing investigations that unsurprisingly sided with his claims. Though modern historians agree both men developed calculus independently, the feud consumed much of Newton's later years and tarnished his reputation for fairness. Newton also faced personal challenges. Known for his solitary nature, he became increasingly reclusive and secretive, especially when criticized. His disagreements with contemporaries such as Robert Hooke, who accused Newton of borrowing ideas on optics and planetary motion, led to strained relationships within the scientific community. His later experiments in alchemy and theology, fields now considered pseudoscientific or philosophical, also sparked confusion among peers. Newton believed deeply in hidden connections between science, nature, and the divine, dedicating countless hours to decoding biblical prophecies and searching for the philosopher's stone. Yet, through these intellectual and personal battles, Newton remained resilient. His ability to confront adversity with relentless focus allowed him to refine his theories and defend his legacy. Even in the face of controversy, his dedication to uncovering the universe's secrets never wavered, securing his place as one of history's most determined and brilliant minds. As Isaac Newton entered the final decades of his life, his role shifted from that of a revolutionary scientist to a revered elder statesman of British science. By the early 1700s, his fame extended well beyond the intellectual elite. He had become a symbol of reason and enlightenment across Europe. In his later years, Newton remained deeply involved with the Royal Mint, where he continued his crusade against counterfeiters with the same rigor he once applied to his scientific inquiries. His reforms stabilized England's economy, and his meticulous attention to detail earned him widespread respect beyond academic circles. Despite his continued prominence, Newton's scientific output diminished. Instead, he focused on defending his earlier work, particularly in his ongoing feud with Leibniz over calculus. Newton even published the Commercium Epistolicum, a series of papers aimed at proving his priority in the invention of calculus, further alienating continental mathematicians. As president of the Royal Society, Newton maintained his influence over scientific discourse, often using his position to settle disputes or promote his own theories. However, this control also made him increasingly isolated, as many contemporaries hesitated to challenge his authority. Privately, Newton devoted much of his time to theological studies and alchemical research. His personal writings from this period reveal a mind preoccupied with questions of faith, prophecy, and the mysteries of the universe, subjects he believed were as vital as his scientific discoveries. By the time of his death on March 20, 1727, Newton had become an intellectual titan, honored as the first scientist to be buried in Westminster Abbey, a resting place typically reserved for kings and national heroes. In his final reflections, Newton humbly downplayed his achievements, famously remarking, "I do not know what I may appear to the world, but to myself, I seem to have been only like a boy playing on the seashore, finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." Isaac Newton's death in 1727 marked the end of an era, but his influence only grew stronger in the centuries that followed. His groundbreaking discoveries reshaped humanity's understanding of nature and laid the foundation for much of modern science. The laws of motion and universal gravitation introduced in the Principia became the bedrock of classical mechanics, providing the mathematical framework to describe the behavior of objects both on Earth and in the cosmos. Engineers, architects, and scientists relied on Newtonian mechanics to build bridges, design machines, and explore the principles of flight. His equations even guided space missions centuries later, helping humans land on the moon. His pioneering work in optics also fueled major technological advances. Newton's theory of color and his invention of the reflecting telescope transformed astronomical observation, allowing future scientists to peer deeper into the universe than ever before. Today's most powerful telescopes, including the James Webb Space Telescope, still employ principles Newton established. In mathematics, though the controversy with Leibniz persisted for years, Newton's contributions to calculus became a vital tool in every scientific discipline, from physics and engineering to economics and computer science. Modern developments in artificial intelligence, quantum mechanics, and astrophysics still rely on mathematical methods rooted in Newton's early insights. Philosophically, Newton's work symbolized the triumph of reason and empirical evidence over superstition and dogma. His scientific method, an emphasis on observation, experimentation, and mathematical proof, became a cornerstone of the Enlightenment, inspiring generations of thinkers like Voltaire and Immanuel Kant. Even in death, Newton's legacy endured as a catalyst for the Industrial Revolution and the dawn of modern technological society. His insights not only transformed scientific inquiry but also reshaped the way humanity viewed its place in the universe, no longer governed by mysterious forces, but by natural laws that could be understood, predicted, and harnessed. Nearly 3 centuries after his death, Isaac Newton's influence remains deeply embedded in modern science, technology, and culture. His revolutionary insights continue to shape the way we understand the universe, and his intellectual legacy endures as a symbol of human curiosity and the relentless pursuit of knowledge. In the realm of physics, Newton's laws remain the foundation of classical mechanics. While Albert Einstein's theory of relativity later refined our understanding of space, time, and gravity, Newton's equations are still used to describe the motion of everyday objects, from falling apples to orbiting satellites. Engineers and scientists continue to rely on Newtonian mechanics for everything from designing bridges to planning space missions. His contributions to astronomy also live on. Concepts derived from Newton's gravitational theories are essential for understanding the behavior of stars, galaxies, and black holes. Modern astrophysics owes much of its foundation to Newton's work, and tools like gravitational simulations continue to reveal the secrets of the cosmos. Beyond science, Newton's influence resonates in philosophy and the development of the scientific method. His insistence on empirical evidence, mathematical rigor, and logical reasoning became hallmarks of the Enlightenment, inspiring thinkers who advocated for rationalism and human progress. The belief that nature operates according to discoverable laws remains central to scientific inquiry today. Newton's legacy also extends into popular culture, with his life and work referenced in literature, films, and art. The iconic image of an apple falling from a tree has become synonymous with sudden insight and intellectual brilliance. Ultimately, Isaac Newton's story serves as a reminder of humanity's ability to unravel the mysteries of the universe. His relentless curiosity, meticulous experimentation, and groundbreaking discoveries continue to inspire scientists, students, and dreamers around the world, proving that even centuries later, the ocean of truth he once spoke of remains vast, waiting for new explorers to follow his path.